Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 412, Fizz Buzz. This classic problem is a great way to practice working with loops and conditionals while implementing simple logic. Let's dive in and explore how to solve it step by step. In this problem, your task is to write a program that generates the string representation of numbers starting from 1 all the way up to a given number, n. However, there are some special rules to follow. If a number is a multiple of 3, instead of the number itself, you output the string Fizz. Similarly, if a number is a multiple of 5, you output Buzz. If a number happens to be a multiple of both 3 and 5, you output FizzBuzz. The input to your program is a single integer, n, which represents the upper limit of the range of numbers. The output is a list of strings, where each string corresponds to a number in the range. The rules for replacing numbers with Fizz, Buzz, or FizzBuzz are applied accordingly, and all other numbers are simply represented as their string equivalents. This ensures that the output will always include n strings, one for each number in the range. Let's look at some examples to better understand the problem. In the first example, if n equals 3, the output list is 1, 2, Fizz. Here's why: the number 1 is not a multiple of either 3 or 5, so it remains as 1. Similarly, the number 2 is not a multiple of 3 or 5, so it remains as 2. However, 3 is a multiple of 3, so it is replaced by the string Fizz. Now, for the second example, where n equals 5, the output list extends to 1, 2, Fizz, 4, Buzz. Let's break this down step by step. In the output for n equals 5, the numbers 1, 2, and 4 are neither multiples of 3 nor 5, so their string representations are unchanged. The number 3, being a multiple of 3, is replaced with Fizz. The number 5, being a multiple of 5, is replaced with Buzz. This demonstrates how the program differentiates between multiples of 3, multiples of 5, and numbers that are neither. Now, let's consider a more comprehensive example where n equals 15. The output list in this case is 1, 2, Fizz, 4, Buzz, Fizz, 7, 8, Fizz, Buzz, 11, Fizz, 13, 14, FizzBuzz. Here's the breakdown of the output when n equals 15. Numbers like 1, 2, 4, 7, 8, 11, 13, and 14 are not multiples of either 3 or 5, so their string representations remain unchanged. Numbers like 3, 6, 9, and 12 are multiples of 3 and are replaced with Fizz. Numbers like 5 and 10 are multiples of 5 and are replaced with Buzz. Finally, the number 15 is a multiple of both 3 and 5, so it is replaced with FizzBuzz. The constraints for this problem ensure that n will always be between 1 and 10,000, and the output list must have exactly n strings. The solution must also be efficient, with a time complexity of O, n, to handle large values of n. Some edge cases to consider include when n equals 1, where the output is simply 1, and when n equals 15, as we just examined. Additionally, for very large n, such as 10,000, your solution must still produce the correct output within the given time limits. To solve the FizzBuzz problem, we are tasked with generating a sequence of strings based on specific divisibility rules for numbers from 1 to n. Several approaches can be considered. The first is the brute force approach, which involves iterating through all numbers from 1 to n and checking each number's divisibility conditions using if-else statements. This method starts by initializing an empty list to store the results. Then, for each number, we check divisibility by both 3 and 5 first to handle the FizzBuzz case, followed by individual checks for divisibility by 3 and 5 for Fizz and Buzz respectively. If no conditions are met, we simply append the number itself to the list. While this approach is straightforward and has a time complexity of O, n, it becomes less practical if additional rules or conditions are introduced in the future, as the logic can become cumbersome to maintain. Next, there is an optimized approach that uses string concatenation to dynamically build the output for each number. This method avoids multiple if-else blocks, making the solution more concise and adaptable. Let's look at the steps involved in this optimized approach in more detail. In the optimized approach with string concatenation, we start by initializing an empty list to store the results. For each number in the range from 1 to n, we begin with an empty string. If the number is divisible by 3, we append Fizz to this string, and if it's divisible by 5, we append Buzz. If neither condition is met, we simply convert the number to a string and use that as the output. This dynamically constructed string is then appended to the result list. This approach maintains a time complexity of O(n), since we still iterate through the range once, but it avoids repetitive checks and nested conditions, making the solution more streamlined. An additional benefit is its flexibility if new rules are introduced, such as adding another string for divisibility by a different number. Minimal changes are required in the logic. Another approach that was considered involves pre-computing modulo results. By creating a lookup table for remainders of numbers modulo 15, we could directly fetch the corresponding output string for each number, which eliminates the need for runtime divisibility checks. However, while this method is efficient, it can feel unnecessarily complex for smaller ranges of n and is less intuitive than the string concatenation approach. Ultimately, we chose the optimized approach with string concatenation because it offers the best combination of simplicity, flexibility, and maintainability. The key insight lies in checking divisibility conditions in descending order of specificity, starting with both 3 and 5, and then checking individually for each. This ensures correctness while keeping the logic straightforward. Using string concatenation eliminates the need for nested if-else statements, resulting in a cleaner and more adaptable solution. This approach operates efficiently at O(n) and is easy to extend if new rules or variations are added to the problem in the future. In contrast, the brute force approach, though simple, is less adaptable, and the pre-computed modulo approach adds unnecessary complexity for this scale. The aha moment came from recognizing that string concatenation not only simplifies the logic but also makes the solution more readable and concise. By focusing on direct concatenation and prioritizing divisibility checks, we achieve an elegant solution that balances readability, extensibility, and performance. To solve the Fizz-Buzz problem, the algorithm follows a series of structured steps. First, it begins with input validation. Here, an integer n is accepted as input, which represents the range of numbers from 1 to n. While the problem guarantees that n will always be a positive integer, it's good practice to ensure n is at least 1 and handle invalid inputs if necessary. Next, we prepare to store our results by initializing a list called result. This list is ideal for holding the output strings because it maintains the sequence of numbers, ensuring the order is preserved. Additionally, appending elements to a list is efficient, with an average time complexity of O(1). Once the setup is complete, the algorithm loops through all integers from 1 to n. For each number I, an empty string called output is initialized. This is where the result for the current number will be constructed based on the divisibility checks that follow. For each number in the range, the algorithm checks its divisibility by 3 and 5. If the number is divisible by 3, we append the word fizz to the output string. Similarly, if the number is divisible by 5, we append buzz to output. If the number is divisible by both 3 and 5, both fizz and buzz will be appended, resulting in fizzbuzz. On the other hand, if the number is not divisible by either 3 or 5, the output string remains empty, and in that case, it is set to the string representation of the number itself. Once the appropriate value for output is determined, it is appended to the result list. After processing all numbers, the algorithm completes by returning the result list, which contains the sequence of strings for the entire range. This approach ensures that all divisibility rules are applied efficiently. The order of checking divisibility by 3 and 5 first is crucial because it ensures fizzbuzz is correctly handled before individual cases like fizz or buzz. The algorithm is designed to handle various edge cases effectively. For example, when n equals 1, the output simply contains the string 1. For n equal to 15, the sequence includes all possible outputs, such as fizz, buzz, and fizzbuzz. For larger values of n, like 10,000, the algorithm remains scalable due to its linear time complexity of O(n). This ensures that the solution can process even large inputs efficiently. Let's also consider the data structure used here. The result list is chosen to store the output strings in order. This choice is ideal because lists maintain the sequence of elements, and appending to a list is both simple and efficient. To see this in action, here's a Python implementation of the algorithm. The function fizz_buzz initializes an empty list called result. Then, for every number in the range from 1 to n, it constructs the output string based on divisibility rules. The final result is appended to the list, and once the loop is complete, the function returns the entire result list. Analyzing the complexity of the algorithm, we see that its time complexity is O, n. This is because the algorithm iterates through all numbers from 1 to n, and for each number, it performs constant time operations like divisibility checks and string concatenation. The space complexity is also O, n, since the result list stores one string for each number in the range, and each string has a constant maximum length of 8 characters for FizzBuzz. There are some potential optimizations to consider. For example, instead of constructing that output string directly, a list could be used to build the parts of the result, which might slightly improve performance for very large values of n. Additionally, if memory usage is a concern, the algorithm could generate and print the output directly without storing it in a list, reducing the space complexity to O(1). While the current implementation is efficient and straightforward, these optimizations could be useful in scenarios with tighter constraints. This implementation solves the FizzBuzz problem by iterating through numbers from 1 to n and applying conditional checks to determine the correct string to append to the result list. First, a list result is initialized to store the output strings. The loop iterates through each number I from 1 to n. For each number, the conditions are checked in sequence. 1. If I is divisible by both 3 and 5, using I%3 equals 0 and I%5 equals 0, the string FizzBuzz is added to the list. 2. If I is divisible by only 3, the string Fizz is added. 3. If I is divisible by only 5, the string Buzz is added. 4. If none of the above conditions are met, the number itself, converted to a string, is added to the list. These conditions ensure that the correct sequence of Fizz, Buzz, FizzBuzz, or the number as a string is appended. Finally, the result list is returned as the output. This approach is efficient with a linear time complexity of O, n, as the loop runs once for each number from 1 to n. The implementation is also clear and aligns directly with the problem's requirements. This Java implementation of the FizzBuzz problem mirrors the logic of the Python solution. The method FizzBuzz accepts an integer n and returns a list of strings. The program iterates through numbers from 1 to n, adding Fizz, Buzz, FizzBuzz, or the number itself as a string to the result list based on the divisibility conditions. Key differences include the use of the list string interface and ArrayList for collection, as well as explicit type declarations and method structure typical in Java. To solve the FizzBuzz problem, we start with an example where the input n is 3. First, we initialize an empty list called result to store our output. Then, we begin a loop that iterates from 1 to n. For the first iteration, where I equals 1, we check 3 conditions, whether I is divisible by both 3 and 5, by 3 alone, or by 5 alone. Since none of these conditions are true for I equals 1, we append the string representation of the number, which is 1, to our result list. At this point, result contains 1. Next, for the second iteration with I equals 2, we repeat the same checks. Again, none of the conditions are satisfied, so we append 2 to the result list. Now, result is 1, 2. Finally, for the third iteration, I equals 3. We again check the 3 conditions for I equals 3. The first condition, which checks divisibility by both 3 and 5, is false. The second condition, I%3 equals 0, is true because 3 is divisible by 3. The third condition, I%5 equals 0, is false. Since the second condition is met, we append Fizz to the result list. At the end of all iterations for n equals 3, our result list contains 1, 2, Fizz. This becomes the final output for this example, demonstrating how we handle numbers up to 3 and decide whether to append Fizz, Buzz, FizzBuzz, or the number itself as a string. Now, let's consider another example where n is 5. As before, we initialize an empty list called result. The loop starts by iterating from 1 to n. For I equals 1, none of the conditions are satisfied, so we append 1 to the result. Similarly, for I equals 2, we append 2. For I equals 3, the condition I%3 equals 0 is true, so we append Fizz. For I equals 4, none of the conditions are met, so we append 4. Finally, for I equals 5, the condition I%5 equals 0 is true, so we append Buzz. At the end of all iterations, the result list contains 1, 2, Fizz, 4, Buzz. This demonstrates how the logic scales as we handle numbers up to 5, ensuring that we correctly identify multiples of 3, 5, and both. Finally, let's examine a larger example where n is 15. After initializing an empty list result, the loop iterates from 1 to 15. For multiples of 3, such as 3, 6, 9, and 12, we append Fizz. For multiples of 5, such as 5 and 10, we append Buzz. When the number is a multiple of both 3 and 5, such as 15, we append FizzBuzz. For all other numbers, we append their string representation. After processing all iterations, the result list contains 1, 2, Fizz, 4, Buzz, Fizz, 7, 8, Fizz, Buzz, 11, Fizz, 13, 14, FizzBuzz. This example demonstrates how the solution handles a range of numbers, effectively determining the correct output for each based on the given rules. The time complexity of the solution is O(n), where n represents the input number. This complexity arises because the program uses a for loop that iterates through all integers from 1 to n, performing exactly n iterations. Within each iteration, the operations performed include modulo calculations such as I%3 and I%5, comparisons to determine divisibility, and a single operation to append the appropriate string to the result list. All of these actions are constant time operations, meaning they take O(1) time individually. When you multiply the O(1) operations within the loop by the n iterations of the loop itself, the total time complexity becomes O(n). Importantly, there are no nested loops or recursive calls in this solution, so the overall time complexity remains O(n), which is efficient given the constraints of the problem. Now, looking at space complexity, the solution is O(n). This is because the program creates a single list, result, which stores the output strings for all numbers from 1 to n. For every number within this range, a string is appended to the list. The size of the list grows linearly with n, as it contains exactly n elements. The space required for each element in the list depends on its content. For numbers divisible by 3 or 5, the appended strings like Fizz, Buzz, or FizzBuzz have a fixed length. For other numbers, the string representation of the number is appended, and its space requirement depends on the number of digits, which scales logarithmically with the number itself. However, since the total number of entries in the list is n, the linear growth of the list dominates the overall space usage. As a result, the space complexity is proportional to n, making it O(n). When comparing this solution to brute force or naive approaches, we find that alternatives would still involve constructing an output list and processing all numbers from 1 to n. This means the time complexity would still be O(n), regardless of the approach. The current implementation is efficient and optimized for the problem constraints. In terms of best, average, and worst-case scenarios, the time and space complexities remain consistent at O(n) in all cases, because the algorithm processes every number from 1 to n without variation. To mathematically prove the big O complexities, we see that the loop runs n times, with each iteration involving only O(1) operations. This confirms the time complexity is O(n). Similarly, the space required for the result list grows linearly with n, and while the space for individual strings varies minimally, the overall growth remains proportional to n. Therefore, the solution achieves both time and space complexities of O(n), making it optimal for this problem. When working on FizzBuzz, there are several common mistakes to avoid. First, using multiple if statements instead of an if-elif chain can cause issues. This happens because each if is evaluated independently, so a number like 15 might trigger both the Fizz and Buzz conditions, leading to incorrect results. Instead, an if-elif chain ensures that only one condition is applied per number, avoiding this overlap. Another common mistake is the incorrect ordering of conditions. If you check for divisibility by 3 or 5 before checking for divisibility by 15, the combined FizzBuzz case will never run, as the earlier conditions will already capture those numbers. The solution is to always prioritize the most specific condition, like divisibility by 15, before checking the more general ones. Additionally, hardcoding range boundaries, such as writing for I in range 101, can limit your solution to a fixed range. It's better to make the range dynamic, like for I in range 1 and plus 1, so the function works for any input n. Lastly, some solutions attempt to handle the FizzBuzz case by concatenating strings like Fizz and Buzz. This can lead to logic errors if the conditions aren't properly managed. A clearer approach is to use explicit checks for each condition, ensuring the correct output is generated for every number. To make your Fizz-Buzz solution even more efficient and robust, consider some additional optimizations. For example, using repeated modulo operations for the same number, like I%3, I%5, and I%15, can result in unnecessary calculations. Instead, you can store the results of these operations in variables and reuse them. This reduces redundancy and improves performance. From an interview perspective, it's important to highlight logical prioritization, such as checking divisibility by 15 before 3 or 5, as it demonstrates clear thinking. You should also discuss edge cases, like handling scenarios where the input in is 0 or extremely large. Moreover, if you're aiming to optimize for larger ranges, you might mention ideas like pre-computing results or using a lookup table. While these aren't necessary for small inputs, they show you're thinking about scalability. Be prepared to discuss variations of the problem too, such as adapting the solution to new rules, like using different divisors or changing the output format. This flexibility can leave a strong impression during an interview. Fizz-Buzz shares similarities with several other problems, which makes it a great stepping stone for tackling related challenges. For example, LeetCode 448, find all numbers disappeared in an array, involves iterating through a range of numbers to identify missing elements, which is conceptually aligned with the range-based processing in Fizz-Buzz. Another related problem is LeetCode 728, self-dividing numbers, which also requires divisibility checks for each number within a range. Similarly, LeetCode 202, happy number, uses iterative logic with specific conditions to determine outputs for numbers, mirroring Fizz-Buzz's step-by-step checks. Finally, while not directly related, LeetCode 118, Pascal's triangle, involves generating structured outputs based on a given range of input values. Exploring these problems can enhance your understanding of range-based logic and conditional processing, helping you build on the foundational concepts introduced by Fizz-Buzz. There are several alternative approaches to solving Fizz-Buzz, each with its own trade-offs. The brute force approach involves straightforwardly checking divisibility for 3, 5, and 15 for each number in the range. While this method is simple to implement, it can be inefficient for larger ranges due to redundant modulo operations. Another method is the string concatenation approach, where you append Fizz4 divisibility by 3 and Buzz4 divisibility by 5, combining them for numbers divisible by 15. This approach can be elegant but may become cumbersome if the rules of the problem change. A more advanced option is the pre-computed lookup table approach, where results for a fixed range, like 1 to 100, are calculated in advance and returned directly. This is memory efficient for small ranges but isn't practical for dynamic inputs where n can vary. Finally, the custom divisor mapping approach uses a dictionary to map divisors to their corresponding strings and iterates through the keys to build results dynamically. This method is highly adaptable to new rules but can be more complex to implement, especially for small-scale problems. Each approach has its strengths and weaknesses, so it's important to choose the one that best fits the problem's requirements and constraints. Great job! To summarize, we solved the Fizz-Buzz problem by using efficient loops and conditional statements. We also reviewed the time and space complexity, and highlighted key programming concepts that can be applied to similar problems. Thanks for watching, and don't forget to subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!